Hello dear students, I welcome you all once again. Today we are discussing the topic chemical constituents of wood. The most accurate definition of wood is a three-dimensional biopolymer composite consisting primarily of cellulose, hemicelluloses and lignin with trace amounts of extractives and inorganics. Water makes up the majority of a living tree's chemical composition, but on a dry weight basis. All wood cell walls are primarily composed of sugar-based polymers, that is, carbohydrates 65 to 75% that are combined with lignin 18 to 35%. Overall, dry wood has an elemental composition of roughly 50% carbon, 6% hydrogen, 44% oxygen, and trace amounts of inorganics. Simple chemical analysis can distinguish between hard wood in angiosperms and soft woods of gymnosperms. However, due to variation within each species and similarities between species, such techniques cannot be used to identify individual tree species. Coniferous species or softwoods typically have higher cellulose content, that is 40 to 45%, higher lignin content 26 to 34%, and lower pantosan content, that is 7 to 14%, than deciduous species or hardwoods, which have cellulose 38 to 49%, lignin 23 to 30%, and pantosans 19 to 26%. Now, let us talk about carbohydrate polymers, that is, holocellulose. Starch and pectin are present in trace levels in wood, while cellulose and hemicellulose polymers make up the majority of the material's carbohydrates. Holocellulose, which makes up 40 to 45% of the dry weight of wood, is a mixture of hemicelluloses, that is 15 to 25%, and cellulose 40 to 45%. Simple sugars such as D-glucose, D-mannose, D-galactose, D-xylose, L-arabinose and D-glucuronic acid make up the majority of these polymers, with smaller amounts of additional sugars including L-rhamnose and D-fucose. Because of hydrogen bonding, these polymers' abundance of hydroxyl groups allows for the sorption of moisture. Now let us talk about cellulose. The most prevalent organic substance in the Earth's surface is cellulose. This glucan polymer is made up of D-glucopyranose units joined by alpha-1,4 glucosidic linkages. Since cellulose's repeating unit is a 2-sugar unit, cellobiose really serves as the building component for cellulose. The degree of polymerization of a cellulose molecule is the number of glucose units in the molecule. The light scattering studies used to determine the molecular weights show that the wood cellulose has an average degree of polymerization of at least 9,000 to 10,000 and perhaps as high as 15,000. A wood sample with an average degree of polymerization of 10,000 would have a linear chain of about 5 micrometers. This would imply that cellulose has a molecular weight that is roughly between 10,000 and 150,000. Cellulose molecules are randomly oriented and have a tendency to form intra and intermolecular hydrogen bonds. As the packing density of cellulose increases, crystalline regions are formed. Most wood-derived cellulose is highly crystalline and may contain as much as 65% crystalline regions. The remaining portion has a lower packing density and is referred to as amorphous cellulose. X-ray diffraction experiments indicate crystalline cellulose in Wallonia ventricosa has a space group symmetry of 16.34 angstrom and 15.72 angstrom. One cellobiose unit or repeating unit has a distance of 10.38 angstrom. There are 8 cellobiose moieties in the unit cell. Weak van der Waals forces hold the layers of packing molecules together. Intermolecular hydrogen bonds hold the parallel chains of anhydroglucopyranose units that hold the layers together. There are also intramolecular hydrogen bonds between the atoms of adjacent glucose residues. Cellulose 1 or native cellulose is the name given to this structure. Wood contains 3 different forms of cellulose. 1. Accessible and non-accessible, crystalline and non-crystalline. The terms accessible and non-accessible celluloses describes how accessible cellulose is to things like water and microbes, while crystalline cellulose is accessible on its surfaces. It is not accessible on its interior. The majority of non-crystalline cellulose is accessible, but some of it is rendered inaccessible by being heavily covered with lignin and hemicelluloses. When it comes to moisture absorption, pulping, chemical modification, extractions and interactions with microbes, the concepts of accessible and non-accessible cellulose are crucial. Another significant form of cellulose that is utilized to create cellulose derivatives is cellulose second. It is not found in nature as cellulose second and is produced by mercerization and regeneration of native cellulose. Using a strong alkali to treat cellulose 1 is known as mercerization. Carbon disulfide is used in regeneration to create a soluble xanthate derivative. The derivative is reprecipitated as cellulose second after being transformed back into cellulose. Space groups of cellulose second are A is equal to 8.01 angstrom, B is equal to 9.04 angstrom, and C equivalent to 10.36 angstrom. Additionally, cellulose third is created by treating cellulose 1 with liquid ammonia at a temperature of approximately minus 80 degrees centigrade, then allowing the ammonia to evaporate. Cellulose second is obtained by alkali treating cellulose third. Heating cellulose third in glycerol to 260 degrees centigrade results in the formation of cellulose 4. Cross and Bavin cellulose is another form of cellulose that is frequently mentioned in the literature, depending on how it is extracted from wood. It is mostly made up of cellulose 1, while some hemicellulose is also present. It is produced by chlorinating wood meal and then washing it with 3% and 2% aqueous sulfur dioxide and sodium sulfite solutions. And lastly, depending on the isolation process, there is another cellulose known as Kirschner cellulose. Wood meal is refluxed 3 times for 1 hour with a 1:4 nitric acid and ethyl alcohol mixture to produce Kirschner cellulose. Kirschner cellulose is the name given to the dried and water-washed cellulose that also includes some hemicelluloses. Because part of the cellulose is destroyed and the nitric acid ethanol mixture has the potential to explode, this method of cellulose extraction is not frequently used. Strong alkalis and most other solvents do not dissolve cellulose 1, while alkali does not dissolve cellulose. It will cause it to swell. Strong acids as 72% sulfuric acid, 41% hydrochloric acid and 85% phosphoric acid can dissolve cellulose. However, the material degrades quickly in these conditions. Because cellulose and lignin and hemicellulose are closely related, it is challenging to separate cellulose from wood in a pure form. Now, let us talk about hemicelluloses. The hemicellulose fraction of wood comprises various polysaccharide polymers with a lower degree of polymerization compared to cellulose, that is, average degree of polymerization of 100 to 200. It predominantly contains sugars such as D-xylopyranose, D-glucopyranose, D-galactopyranose, L-arabinofuranose, D-mannopyranose, D-glucopyranosyaluronic acid and D-galactopyranosyaluronic acid along with minor amounts of other sugars. To understand the structure of hemicelluloses, one should first consider the conformation of the monomer units. Each entry in the figure provides information on the standard configurations of these monomers, distinguishing between D and L forms, which denote the orientation of hydroxyl groups at specific carbon positions in pentoses, that is xylose and arabinose, and hexoses, that is glucose, galactose and mannose. Hemicelluloses are closely associated with cellulose and contribute significantly to the structural framework of the tree. Under conditions of stress, such as in compression wood, certain hemicelluloses are found in large quantities. Compression wood exhibits higher levels of D-galactose and lignin content compared to normal wood. Hemicelluloses typically feature a backbone composed of repeating sugar units alpha 1 to 4 with additional branching points at 1 to 2, 1 to 3 and or 1 to 6. They commonly consist of multiple types of sugar units, often named based on the sugars they contain, such as galactoglucomannan, arabinoglucouronozylin, arabinogalactan, glucouronozylin, and glucomannan. Hemicelluloses also incorporate acetyl and methyl substituents. These polysaccharides are soluble in alkali and readily hydrolyzed by acids. Gradient elution using varying alkali concentrations can crudely fractionate hemicelluloses from wood, followed by precipitation through acidification with acetic acid. Further treatment with a neutral organic solvent like ethyl alcohol yields more efficient precipitation. While the detailed structures of most wood hemicelluloses remain undetermined, studies have focused on determining the sugar composition ratios within these polysaccharides. Now let us talk about hardwood hemicelluloses. This type of hemicellulose is commonly known as glucuronoxylans. It consists of a xylene backbone made up of D-xylopyranose units linked beta 1 to 4 with acyl groups typically located at C2 or C3 of the xylose units, averaging around 7 acetyls per 10 xylose units. The xylene is further modified with side chains composed of 4-orthomethyl glucuronic acid units attached to the xylene backbone alpha 1 to 2, occurring at an average frequency of approximately 1 uronic acid group per 10 xylose units. These side chains are relatively short. Additionally, hardwoods contain a glucomannan comprising beta-D-glucopyranose and beta-D-mannopyranose units linked 1 to 4, constituting approximately 2 to 5% of the hemicellulose composition. The ratio of glucose to mannose can vary between 1:2 and 1:1 depending on the specific wood species. Now let us talk about softwood hemicelluloses. One of the predominant hemicelluloses is galactoglucomannan, constituting approximately 20% of the composition. It features a linear or slightly branched chain composed of D-galactose, D-glucose, and D-mannose units linked by beta-1,4 bonds. The polymer exists in two fractions distinguished by their galactose content. A low galactose fraction with a ratio of about 0.1 to 1:4. Galactose is to glucose is to mannose, and a high galactose fraction with a ratio of 1:1:3. Single unit side chains of D-galactopyranose are attached via alpha 1 to 6 bonds, while acyl groups substitute the second and third positions of the backbone polymer, averaging 3 to 4 hexose units per substitution. Another significant softwood hemicellulose, arabinoglucouronoxylane, makes up 5 to 10% of the composition. It consists of beta 1 to 4 xylopyranose units with D-glucopyranosyl-uronic acid branches occurring on average every 2 to 10 xylose units. Additionally, alpha 1 to 3 branches of L-arabinofuranose are present on average every 1 to 3 xylose units. In the hardwood of branches, another hemicellulose known as arabinogalactan is found. Its backbone comprises beta 1 to 3 linked D-galactopyranose units, with nearly every unit bearing a side chain attached to carbon 6 of beta-D-galactopyranose residues. These side chains may consist of beta-L-arabinofuranose linked 1 to 3 or beta-D-arabinopyranose linked 1 to 6. Softwood also contains minor hemicelluloses primarily composed of L-arabinofuranose, D-galactopyranose, D-glucopyranuronic acid, and D-galactopyranuronic acid. Now let's talk about other minor polysaccharides. Both softwood and hardwoods contain trace amounts of pectins, starch, and proteins. Pectin, a polysaccharide polymer composed of repeating units of D-galactouronic acid linked alpha 1 to 4, is primarily located in the membranes within the bordered pits between wood cells and in the middle lamella. Microbial degradation of these membranes enhances the wood's permeability to water-based chemicals like fire retardants and preservatives. Pectins are also concentrated in the parenchyma cell walls of the inner bark, where they serve as binding agents. Minor components of pectin substances include L-arabinofuranose and D-galactopyranose. Pectin can also exist as a methyl ester. Starch functions as the principal reserve polysaccharide in plants and is present in small amounts within wood cell walls. It typically appears as granules consisting of D-glucopyranose units linked alpha 1 to 4, that is amylose, or alpha 1 to 4 with branches occurring approximately every 25 glucopyranosyl units at alpha 1 to 6, that is amylopectin. Amylose adopts a helical structure in its solid state due to the alpha configuration within the polymer, whereas amylopectin is highly branched. Dear students, let's now talk about lignin. Lignins are amorphous, highly complex, mainly aromatic polymers of phenylpropane units that are considered to be an encrusting substance. The three-dimensional polymer is made up of carbon-oxygen-carbon and carbon-carbon linkages. The precursors of lignin biosynthesis are paracoumaryl, coniferyl alcohol, and synapyl alcohol. Lignin does not have a single repeating unit like cellulose of the hemicelluloses, but consists of a complex arrangement of substituted phenolic units. Lignins can be classified in several ways, but they are usually divided according to their structural elements. All wood lignins are primarily composed of three fundamental building blocks: gausyl, syringyl, and para-hydroxyphenyl moieties, although other aromatic units are also present in various wood types. There is significant structural variation among different wood species. Hardwood lignin content generally ranges from 18 to 25%, while softwood lignin content ranges from 25 to 35%. The phenylpropane units can be substituted at the alpha, beta, or gamma positions, forming various combinations through ether and carbon to carbon linkages. Softwood lignins predominantly consist of polymerized coniferyl alcohol known as gausyl lignin. In contrast, hardwood lignins termed syringyl gausyl lignin are copolymers of coniferyl and synapyl alcohols. The ratio of coniferyl and synapyl alcohols in different lignins varies, ranging from 4:1 to 1:2. Wood lignins contain significant amount of constituents beyond gausyl and syringyl propane units. Lignin is distributed throughout the secondary cell wall with the highest concentration in the middle lamella. Due to the difference in volume between the middle lamella and the secondary cell wall, approximately 70% of the lignin is located in the cell wall. There are various methods to isolate lignin from wood. Classon lignin is produced by hydrolyzing polysaccharides with 72% sulfuric acid. This type of lignin is highly condensed and does not accurately represent lignin in its native state. An alternative method uses enzymes to remove polysaccharides, yielding enzyme lignin, which more closely resembles native lignin. Milled wood lignin, also known as Jorkman lignin, can be isolated by using a vibratory ball mill on fine wood floor and extracting with appropriate organic solvents. This method isolates about 30 to 50% of native lignin, although it is labor intensive. The molecular weight of lignin varies with the extraction method. Classon lignin, being highly condensed, has molecular weights ranging from 260 to 50 million, while Jorkman lignin has a molecular weight of around 11,000. Lignins often associate with hemicelluloses, forming lignin carbohydrate complexes that can be resistant to hydrolysis even under pulping conditions. There is no evidence that lignin is associated with cellulose. Now let us talk about extractives. Extractives, also known as natural products, are chemicals found in wood that can be extracted using various solvents. These extractives are sometimes categorized based on the solvents used, such as water-soluble, toluene, ethanol-soluble, or ether-soluble extractives. Numerous extractives have been identified, and while the functions of some are well understood, the presence of others remains unclear. Historically, extractives like pine pitch and resins have been utilized for waterproofing wooden boats, as components in torches, and as binders. Extractives have also been used in medicine, cosmetics, and as preservatives. Some extractives in wood serve as precursors to other chemicals, while others are produced in response to wounds or function as defense mechanisms. These extractives, primarily comprising fats, fatty acids, fatty alcohols, phenols, terpenes, steroids, resin acids, rosin, waxes, and other minor organic compounds, can exist as monomers, diamers, and polymers. Generally, softwoods contain higher levels of extractives than hardwoods, with most extractives in both types located in the heartwood, contributing to the wood's color, smell, and durability. The qualitative variation in extractive content among different species forms the basis of chemotaxonomy, which classifies plants based on their chemical constituents. Resins and fats consists of resin acids and fatty acids respectively. Fatty acids are esters with alcohols like glycerol and are predominantly found in sapwood. Resin acids, characterized by a free carboxylic acid group, are primarily located in the heartwood. Abietic acid represents a common type of resin acid. Among softwoods, alpha-pinene is the most prevalent terpene, along with structurally similar compounds. Pinosylvin, a potent polyphenol found in pine heartwood, is known for its toxicity. lignans formed by combining two phenylpropane units are widespread in softwoods, with conidendrin being notable in spruce and hemlock. Wood tannins fall into three main classes: gallotannins, allagitannins, and condensed tannins. Gallotannins, polymeric esters of gallic acid, are typically associated with sugars. Tropolones such as alpha, beta, and gamma thujaplicin contribute to the durability of cedar wood. So, dear students, here comes the end to this discussion. I hope you have grasped the essence of this talk today. Thank you for your unwavering attention.